Okay, friends, we're going to look at the last section in related rates. This is related rates part 3, and hopefully this video helps you have a deeper understanding of what we are looking at. I chose this image here. I think it's a really interesting image of this beautiful trestle bridge over this canyon below. And so today's question involves a trestle bridge and a canyon. I want to just make sure that you're aware that the curricular competencies in related rates, you're basically flexing all of them. You're not flexing them so much by listening to this video. All that you might be flexing there would be, perhaps perseverance and staying with my explanation, or, maybe some of your analysis of what I'm saying for you, trying to make connections between what I'm saying and the problems you're thinking of when you're working with other people and wrestling on your own without these supports. Really, you're accessing and flexing all the curricular competencies. So here's today's challenge, and it is really a tricky one. A horse on a bridge is 6 meters above an otter in the river below. The river and the bridge are perpendicular to one another. The horse starts running south at a rate of 8 meters per second, and the otter swims east at a rate of 5 meters per second. Determine the rate at which the distance between the two animals is changing. First things first, before you set the video on pause and try this on your own, is let's just make sure we all agree where north and south is and where west and east are. Okay, so pause the video right now, try this video, set a timer for 10 minutes, 15 minutes, 20 minutes. You're practicing your perseverance, you're practicing being curious, you're wondering, you're noticing, you're trying to make connections between the information that's before you. Okay, so let's take a look. Okay, I hope you've paused the video, and let's take a look. So here's the idea. Okay, so you have this horse and it's running along a bridge. This horse is 6 meters above the water. Okay, so that would be at right angles vertically. And then there's this otter and it's going like that. Okay, so we have this otter that's moving. So we have, I think this is going at 8 meters per second. I'm not sure how fast that is for a horse, 8 meters per second. That sounds pretty dang fast. That's a fast horse. The otter, I believe, is moving at 6 meters per second. And gosh, if you look at this, it sure looks like it would be really tricky to kind of figure out how these are connected. And so what you have to realize is, remember, from the top view is we have, south is going this way and east is going this way. And then you also have to realize that, this is difficult to visualize, but then this is the aerial view. And then directly below that is, these are separated by a vertical distance. So that's what this is trying to represent. So I'm going to attempt to make this look that way and see if this helps. So I'm going to do this. I'm going to do that. I'm trying to give it the idea that this is actually a three-dimensional challenge. And I hope you can start to see that reality here that I just erased, unfortunately. So we have this distance, and this distance. Okay, I'm going to make these distances connected. So it looks like that, and okay, and what we're trying to find is the distance between where the horse is a few seconds later to right there. That's what we're trying to find. And if we were to label this, here's my horse, and there the horse is moving south, separated by a height, because remember, this H and this H are the same, and then we have the otter who's moving east, and we're trying to find out the diagonal. Okay, it might be helpful for you to visualize by creating these diagonals here so that you can see that red distance, right, that red diagonal is the diagonal of that orange sheet. But we also have a formula that we've learned recently, which is that d squared, the distance of the diagonal of a cube or a rectangular prism, equals s squared plus h squared plus e squared. Okay, and at this point, it might be a good idea to write down all the variables. So h, h prime, e, e prime, and b, b prime. Okay, and I recognize that I changed that. So the b is, for some reason, I called the horse b. rather than h. So I think that's a poor choice for letters myself, but that's what I did. Okay, so then we have this equation right here. Now we're going to take the derivative of each of these with respect to time. So the derivative of d squared is 2d d prime, and h squared is 2h h prime, and so on. Each of these have the possibility that they might be changing with relation to time. And I can see that I have this guy. I have all of these. These are all known. They're all given. The only thing that isn't given is the d, which I do need to find. And since I have these variables here, I could plug them into there to figure out what d is by Pythagoras. So that's why you're going to see that square root there, because that's just the Pythagorean theorem of a rectangular prism. So by putting h, e, and b in, you can figure out what d squared is and then square root it. Notice that we know that h is 6, that e is 10, and we can fill out those variables. And then at this point, it's just an algebra problem where you're going to be rearranging and solving. Okay, and so that's what it is. We're going to divide both sides by that, leaving d prime on its own, and that's the approximate solution. So obviously, no question, this was a difficult problem, and the biggest challenge for you would have been to make sense of this 3D situation. But you remember that we spent a day reviewing ideas like Pythagoras and similar triangles for this very fact. So this is a skill we have done before, and hope this clip helped you understand that better. Okay, on this slide here, let's take a look at this. This is another tricky problem. I'll read it to you and then pause the video and set yourself up for another 10-15 minutes on your own. The base of an isosceles triangle is 10 centimeters, as noted, and is not changing, noted. Both equal sides are growing at a rate of 2 centimeters per second. So that means that as seconds go by, it's going to look like this. And as more time goes by, it's going to be taller and so on. Okay, so we should start thinking about that. Okay, determine the rate at which the area is changing when the area is 60 centimeters. Okay, this is a freaking tricky question. So let's take a look at it. Okay, first off, let's label it. From our question, we knew that the base was 10. The height is h, and we labeled it h. I'm going to call each of these side lengths x because they're the same and they're growing at a rate. Now the question is, let's make sure I know what the question is. Determine the rate at which the area is changing when the area is 60 centimeters. So the very first thing I should be doing here is area equals base times height divided by 2. Okay, that's what we need to do. Now, this is quite a tricky question, but at very first glance, so what I should be doing is saying things like A prime, B prime, and H prime. Oops, I don't need that little guy there. So don't need that, okay? And just as another observation is we already actually know what the base is. The base is 10. So right off the bat, I could say that this is area equals 10h times or divided by 2, which equals 5h. So really, this has really been a simplified question because the base isn't changing. Therefore, I could put base in right away. Let's see what happens in the explanation. Notice that I know what the area is at a certain point. It was 60. We're trying to find this guy. So that's the question right there. Okay. Base is 10. B prime is 0. We don't know what h is. We don't know what h prime is. We do know what x prime is, and we don't know what x is. So obviously, this is a really tricky question. And once again, we don't have enough information. In fact, we don't know anything about h. So this should give us the hint that we need to make a move here. We need to make some sort of change. And notice right here that area equals 5h. So really what I need to do is find some way of representing h. And I don't know anything about h. So I hope what you're going to be about is redrawing this triangle, calling this h, calling this x, and then calling this base, this distance here, 5. We could then, by Pythagoras, I think this is how we want to do it. There might be 2 ways of doing this. So let's follow this path and see where it gets us. Okay, so I'm going to say that x squared equals h squared minus 5 squared. So that means that the square root of x squared is going to give me h squared. I solved the wrong way too. Shoot. I don't care what to isolate for x. I want to isolate for h and get rid of h, okay? So if I do this, I'm going to have x squared equals h squared plus 5 squared, okay? And then I'm going to rearrange. So h equals the square root of x squared minus 25. And remember earlier, we said that the area equals 10 over 2 times h. In other words, area equals 5h. Okay, so we can now substitute that in for h right there. Okay, and so I think that's probably what we're going to see here. And so that's what we're doing. We're going to sub that in. So we're going to have our 5 here. And now what we need to do is take the derivative. And so we'll do that. So we're going to be careful here. We're going to use the chain rule. So the power rule comes down to the power negative 1/2, and then the derivative of the internal function, which is going to be 2x times x prime, right? So the derivative of this is 2x, and the derivative of x is x prime. Many of you will have forgotten to do that. So this is the chain rule, so pay attention carefully to that. Okay, then we can rearrange this. Notice that we're going to have simplify 5 times 1 times 2x, which would be 10x, and on the bottom we'd have 2, so those would cancel, leaving me with 5x. Another way of saying that is that 2 and that 2 would cancel. So we'd end up having 5x over this, and now we need to sort of just go for it. Okay, so now let's look at this. Do we know what x is at any given time? We don't. Oh my gosh. So we need to keep on wrestling with this. We thought we were out of the fire here, but we're not. What we need to do, I guess we know what each x prime is. We know what that is, so that's good news. But we don't know what x is. And we need to go back to the question and remember that they told us that at a certain point, what's the rate of change when the area equals 60? So area equals, so when the area equals 60, we would know what we could use that to find out what x is, okay? Because we know that right here, where was it? Right here, we know that that equals 60. Okay, so let's just make sure I'm making sense here. So we know that h would equal 12. Yeah. Okay, so we just went 60 equals 1/2, and we found out that h equals 12. So we could say that 12 equals this distance here. And there might be other ways of thinking about this. But when we do that, we know that we can figure out, oh my gosh. So right here, I go back to this guy right here. Put h equals 12 in there, and we can use that to figure out what x is. And so that's what happens. So to put it another way, this has been a bit of a jumble of my explanation here for sure. If that's 12 and that's 5, by Pythagoras, we can figure out what x is. Okay, and when we do that, we find out it's 13, sneak 13 in there, sneak 13 in there, and you'd be done and out the door. Okay, there may be other ways of finding this solution. So if you find another solution, you should definitely put that in your digital portfolio as evidence that you can think creatively and you're open to different solutions. Okay, and I would like you to assess your ability in drawing great pictures. And remember, a proficient example of a drawing is one in which we could totally erase the initial question, and by looking at this information here, we would know what the question was. Okay, so we're going to end the video right there, and I hope it was helpful. Best of luck.